Okay, so welcome back everyone. Now we are going to start the third session of this tutorial where we have Rishabh Singh and Xingming Chen later to tell us about program synthesis techniques and also the applications to artificial intelligence tasks. So our next speaker is Rishabh Singh. And Rishabh Singh is a research scientist in the Google Brain team where he works on developing new deep learning architectures for learning programs and program analysis. So he developed new program synthesis techniques for helping end users, students, and programs. And apart from research, he enjoyed playing bridge. Okay, now let's welcome Rishabh.
Okay. Awesome. Thanks a lot, Judge. Johan. Actually, can you see my screen? Or
Yes.
Oh, great. Let's get started. Again, thanks a lot for the kind introduction. And today I'm actually excited about talking more about how we can build program synthesis techniques that actually get inspiration from how humans write programs. And actually, just to get started, and many of the presenters before have already mentioned this interesting perspective of looking at machine learning from the lens of program synthesis, where we're given some data, some specification, and then instead of learning some machine learning model, we instead learn programs. And as we saw previously, there's some very nice properties of learning programs in the sense that because they come from a fixed set of abstraction or symbols, they can learn to perform much more complex tasks. In addition, actually, because of the strong prior we have in the design of the language itself, they tend to generalize much better than just training the standard machine learning algorithms. And finally, as we also saw earlier, these programs are more interpretable, so we could edit them in future if we want. So that's why there's lots of interest in learning programs from different types of data. There's actually one more domain where actually make advances in program synthesis, where we can help make programming much easier and really democratize it. And by it, what I mean is that actually we can enable to lower the barrier of programming and help people who may not have all the expertise in writing programs, but they still want to do such programmatic tasks and enable them to do such tasks from simpler specifications. Now, actually, one way to think about program synthesis is that it's a big search problem where I have a space of programs, I have a programming language, and I would like to search for a program that satisfies the specification. And we have had lots and lots of great progress in recent years, in particular using state-of-the-art theorem provers or SAT and SMT solvers, as well as developing custom search algorithms to be able to efficiently search this large space. But one of the biggest challenges still remains that although we have made lots of progress, we still can only synthesize programs of limited size, as well as uh, in very limited domains, in the sense these are not general purpose programs. So there's still actually a, a big barrier in generalizing these techniques to be able to learn programs in more general and more complex programs. Now, actually, one thing actually we can think about is that this task of programming, even though it's very complicated, human programmers routinely write programs, like all of us. We are able to take specification in many different formats, let's say natural language, imperfect examples, and are able to write programs that satisfy that specification. Here's my 3-year-old niece writing Python programs. So actually, if you were to step back a little bit and think about how human programmers are able to write such programs, it's not really the case that we are actually doing search, which is typical way of doing synthesis uh, currently. And actually, if we go inside and think a little bit more about what type of abilities people might be using. So first is actually we need to do some logical analysis, some reasoning to say for this problem, here are like the components I would like to use, and this is the logic I'm going to use to solve this task. And then it's also the case that not all human developers are great programmers from the beginning. We all learn programming, we learn the basics, we then practice, and over time actually we improve. And finally, it's not the case we always write programs from scratch. We are able to learn to also use other components. For example, some of the things in the previous talk, Kevin was mentioning about libraries. So oftentimes, actually, instead of learning programs from scratch, we learn to use libraries as well. So one of the ideas is that can we bring these types of capabilities into these learning-based models to be able to build systems that can hopefully scale better or learn more general tasks. So in this talk, actually, I'll go a little bit in more details about some of the things which have this notion of how human developers write programs, and we'll see some examples in ways we could use these intuitions in building up these architectures. So first main point, as already mentioned, is that human developers seldom actually do search. We have this notion of intuition, this notion of saying that for this task I'm going to use these types of libraries, and this is how my structure is going to look like for the program. So that's one interesting point of these capabilities compared to search-based systems that typically do program enumeration. Another thing about these synthesis systems is that typical search-based systems are static, in the sense we develop a system for once and that's what we get. Whereas humans actually, as we solve more problems, we get better. So can we build systems that also have this capability that as we write more programs in different domains, actually we increase our capabilities, we get better over time. Um, Another interesting thing is that human developers are able to ingest specification in many different forms. So for example, in natural language, in proper examples, partial programs, unlike typical search-based systems that support typically one mode of specification. The other interesting part is that human developers typically take a big problem, big programming task, and divide it into smaller sub problems, write programs for the smaller tasks, and then learn to compose them to solve the bigger task. So that's another interesting capability that we as humans typically use to write really large pieces of programs, which potentially we could use as well. And finally, I think this is also an interesting point where most of the synthesis systems that are search-based actually by construction are built to generate programs that are correct by construction. Whereas actually when we write programs, it's seldom the case that we get the program right in our first attempt. So we typically test them, we edit them, we modify them over time from our first attempt. So actually, these are some of the ideas we're going to see in this talk about how can we take inspiration from these things and build some of these ideas into the architectures. So actually, let's get started with the first point about doing explicit search versus what I'm calling intuition-based program writing. And for this, I'm going to use a system called RobustFill. This is built on top of a system a few years back we built um, called FlashFill, which is a programming by example system for spreadsheet users. So here the idea is users can give examples, in a few improper examples of what they would like the system to do. And in the backend, the system would learn a program uh, that can then be run on the remaining entries in the sheets to finish their task. So in this system, actually, we developed a very custom built system based on using some domain insights. So the way the system works is we have a small programming language, and it's designed in a way that it's expressive for many of the tasks people want to do. And it typically involves some kind of regular expressions and some constant strings in their compositions. So one example task would be, let's say a user wanted to convert names to last name, comma, first initial. And one way to describe this task in the language would be that I want to concatenate four expressions, where first expression is a regular expression to get the last word, followed by constant comma space, followed by first character, followed by dot. So this would be a way to write this logic in the language, backend language. But we don't want people to write such programs. We would like users to give examples and have the system generate the program for us. And actually, we're going to use this more general mechanism for learning programs, which we'll see later in the talk also in other domains. It's going to be quite similar. And the way this is going to work is we're going to start with a language, which I'm calling DSL here. we are going to sample programs from this language to generate training data, as well as corresponding specification input of examples. We're going to train models from this data, and then utilize the program semantics. We'll get to it, like what do we mean by semantics. But the nice thing about programs is that we are able to execute them. We are able to do analysis on them, which could then be used to perform more reasoning on top of the learned distribution. And the output of this whole framework would be a synthesizer, which when we give examples, it would hopefully return programs for us. So just to get a little bit more concrete about the synthetic dataset generation. So for example, in this language I was showing you earlier, we can sample random programs. In this case, I'm saying, okay, give me a program that concatenates third alphanumeric token followed by string starting from first colon, followed by first four characters. So it's a random program we sampled from the language. We can sample random inputs, run the program to get outputs. So this way we can get input-output program pairs and millions of them. So we can have a real curriculum of programs that are really simple to programs that are very complex. And this data set we can use to train our models. And then actually, we're going to train it on synthetic data, but then we're going to test it on real data in terms of the tasks that real spreadsheet users want to do. And the hope is if the system has really learned the right concepts about these regular expressions or these compositions of programs, then hopefully it can generalize to also be able to learn programs on inputs that it has never seen before. And at very high level, I guess some of the talks also we saw, the architecture is going to be this encoder-decoder based architecture, where we have one component that embeds examples into latent space, and the second component that's going to take this latent representation of examples and generate programs. And there could be multiple different ways to decode. We'll see some examples later. So for robust fill task, where our goal is to go from input-output strings to programs, the particular encoder we use is something like seek to seek to seek, where we first have a bidirectional LSTM that embeds input strings. We embed the output string, again using another bidirectional LSTM that attends over the input string as well as is conditioned on the input's latent state. And finally, we have a program decoder, which is another sequence model that attends over both inputs and outputs. So this is how we can embed one example. And then we have, in our case, a user might give multiple examples. And the way we combine them is by first having individual embeddings for each program corresponding to each example, P1 to Pn. And then we do some pooling operation to get a final program representation with the intuition that this pooling operation is doing some type of intersection that I want to learn a program that is consistent with all the examples I've seen till now. So basically now we can train this architecture end to end on the synthetic data I was showing you earlier. And then we can test it on real data. And it actually, for this case, we found that after enough training and using the right curriculums, the model was able to do quite well on real data. It gets to about 92% tasks that could be solved. And this was actually even higher than the one system we wrote manually for the earlier version. And which is kind of interesting because the model, in addition to learning the correctness that I want to learn a program that is consistent, it's also able to learn some implicit ranking also, which is quite nice. Actually, one quick side note I wanted to also share here was that the power of having symbols or grounded abstractions. So we could treat this problem without having a language as well. So we can say, I'm not going to have this latent program representation. I'm just going to have inputs and outputs. And the goal is that given some examples and a new input, the network directly has to produce the output. So which is what I'm calling induction here. Whereas in synthesis, actually the network produces a program. And one thing we observe is that because we have symbols that are being produced, we could execute them and analyze them, which is not the case in the induction setting, where we only have a generative model of characters, and we could do a little bit of beam search, but not a lot. So that's also a power of having symbols in the reasoning space. Great. So actually, let's quickly now get to the second point I wanted to show, where instead of having a static synthesis system, can we build systems that improve over time? And similar to humans, when we solve more problems, we actually learn more things. And for this, I'm going to use an example called Karel. Karel is a small programming language designed to help students learn programming. So this is typically taught on hour of code courses, as well as it's also taught in introductory programming classes at Stanford. And the goal here is that there's a rectangular grid and a robot named Karen, and it has to move around in the world by picking markers or putting markers to accomplish some task. So in this case, for this example, the robot has to use a while loop or a repeat loop to come up with this pattern. So similar to RobustFill, actually, there's also an underlying DSL here. The nice thing about this DSL, interesting part is that in addition to just functions, it also has control flows. So it has notions of while loops and if conditions, and and that poses a different set of challenges for the network to learn in this setting. And that's something we wanted to also explore, that how well these approaches work when we have more complex control flow and data flow. So similar to RobustFill, actually, we can generate random data, synthetic data by random sampling. Here it's a little more involved just because of the presence of loops and everything. So we can use some automated program reasoning techniques to generate programs that or examples that cover all branches. But here also we need to be slightly more careful about the distributions we are sampling. And in this other paper, actually, we explore in more details how we can generate more uniform data sets. And if you're interested, that would be a great source to read more. But for now, actually, let's assume we are able to generate training data like RobustFill here of programs and input examples. So again, we're going to use similar architecture of encoder-decoder. The only difference here would be that instead of using a bidirection LSTM-based encoder, we here use CNNs because we uh, because the inputs here have slightly more visual nature, and the network might be able to learn something about uh, looking at the images or the visual structure in the input examples to know when to use while loops or when to use if conditions. And our decoder in this case again is still a sequence model. So we can train it like RobustFill here again, end to end on the synthetic data, and it does reasonably well. Now, but one problem here is that during training, since we are doing supervised training, we are forcing the network to learn one specific program per example, whereas improper examples are in under specifications. So there could be multiple programs that are consistent. But right now, we are penalizing the model to produce the same program. So in this case, the idea was actually, can we go beyond just supervised training, actually train the model based on the output of the program rather than the syntax itself. So for that, actually, we came up with some simple algorithm. Here, the idea was we first train the model in a supervised way, like robust way. Then what we do, we sample, given some example problem or imperfect samples, we sample a program from this distribution and we execute the program on the inputs to get the corresponding outputs. And now we do a simple check whether the output is same as the expected output. And if it is, then we give it a small reward to say, yeah, this is also a good program. And make sure actually in future to consider this also as a positive example. And if the output doesn't match, then we give it a negative or zero reward to avoid generating those programs in future. So this is a simple way to actually add um, this concept of adding more program semantics in the search to say it's okay to generate another program different from what the training dataset has, as long as it produces the right output. And by adding this additional uh, reward mechanism, we saw that the model actually is able to solve more tasks and sees an improvement of 5 to 6% on the test set. Great, yeah. So this was briefly about how we can build systems that can go beyond just supervised training. Now, let me talk briefly about this other two capabilities that human developers can look at specifications in many different forms. as well as this notion of breaking down a problem into sub-problems and learning compositions. So for this, I'm going to use another system that we have recently been building. It's called TFCoder, and this is for helping programmers write tensor manipulations. And in this case, we'll use TensorFlow as an example, where the idea here is that actually when we are building machine learning pipelines, we have to do a lot of manipulations on tensors using a set of APIs, let's say like tf.gather, tf.scan, and everything, which actually might pose new challenges, for, especially for beginners who may not have expertise in these types of APIs. And typically, what users do right now is when they have such problems, they go to help forums like Stackoverflow. In this case, they're asking a question that I have a tensor like this, and I would like to get a tensor like this, but I'm not really sure exactly which functions to use and how to compose them or what arguments to use. And typically what happens here is that after users post these problems, some experts come in and then they answer users' query. And in this case, actually, for this example, this answer was produced incidentally by TFCoder itself. And it can answer such questions by saying, maybe you would like to use this program to do this task. One interesting component here is that when experts look at these problems, the specification comes in both, as we were saying earlier, it has both natural language component as well as input output examples. So TFCoder also has exactly same interface where it treats the natural language as well as examples, and then actually generates a program in using TensorFlow APIs that is consistent with the examples as well as some notion of natural language. Now, to build this system, actually, we're going to use again similar concepts. We're going to have two learned models. One that maps examples to distributions over TensorFlow program or APIs, which is similar to Robustville and Karel. So I won't go into too much details, but we can sample random programs, random APIs to train such a model. For natural language, it's more tricky because we can't synthetically generate them. So, and also there's not a lot of data of how human programmers write natural language for these APIs. So for that, what we do is we right now use documentations of these APIs. So for example, tf.scatter nd, we have some natural language description of what this API does. We build an embedding of the API based on its documentation. And then we construct an embedding for the question that the user is asking, and then do some kind of uh, distance measures using a cosine similarity of the full embeddings of the natural language descriptions and the APIs to learn likely APIs that might be useful. So actually, once we have those two models, the basic idea of the synthesizer is that we use those distributions to first build small programs. So you can imagine we first build TensorFlow APIs using one function at a time. And then we assign them weights using the model. And then we start to learn to compose them. So we would say, actually, let's now try to compose these two APIs based on the learned distribution, and slowly, incrementally building up the program that hopefully at the end is consistent with what the examples users provided. And it turns out actually once we do this type of bottom-up compositional uh, uh, synthesis of programs, it not only solves more tasks than typical search-based methods, but it's also much faster. It's about 38% faster in synthesis time as well, which is also quite nice that these models can guide the search to be much faster. Great. So finally, I want to briefly talk about the final point on how humans, when we write programs, it's seldom the case that we write correct program in our first go. So here, the idea is actually can we allow the synthesizer to make mistakes and then have a mechanism to correct it. So for example, actually, if we go back to the previous example we're looking at, let's say we are in the robust field setting and we're given some examples and the synthesizer learns a program like this, which is almost correct, but it makes a small mistake in the sense it learns to extract a second word instead of and this logic actually works well for rows 1, 3, and 4, but for the second example input, it extracts M rather than Myers. So the idea is actually in robust fill, the way to fix this problem would be we can sample more programs from the distribution and evaluate them to see if any one of them actually is consistent with the outputs. But a better approach would be actually maybe similar to how we humans, when we debug these programs or test them, we execute these programs to get corresponding outputs, and then we actually know that this is what the current program is generating, and this is what the expected output is. Can I make fixes to the original prediction? And in this case, when we give it to the model is able to correctly modify the logic of learning second word to the last word, which is in this case the desired program. So at very high level, the way this architecture works is it's similar to robust fill in the sense we start with some examples. We have some example encoder. We put the we embed the examples into some latent space, and then we have a program decoder that decodes this latent back to a program P, let's say. And that's where this fixer comes in. So we feed this program back to an execution engine that's going to run this program on the examples, and it will produce new outputs. Let's call them PI0 and PIN. And then once we get this triplet, if the outputs are exactly the same as the original outputs, then we are done. We return back the program. Otherwise, we take these triplets of initial examples and the current outputs. We have another encoder that embeds these triplets. We put it back into the original latent space. And then we have another decoder that decodes this latent back to a program, let's say P prime. So during training, we can train it in this way. But at test time, actually, what thing we can do is we can call this fixer iteratively. So we can first get first program P1, then if it works, great. If it doesn't, we call our fixer again until we get to a program that actually works. So very briefly, in terms of actually accuracies, we do see quite a decent jump on learning programs more accurately compared to just using robust fill. But interestingly, actually, when we do qualitative analysis about how does beam search compare to this type of fixer approach, we find that fixer is actually able to make many more changes to the original program, whereas beam search does a smaller number of changes. And also it's able to make changes into the early parts of the program, whereas beam search typically does, as expected, makes changes towards the end of the program. Great. So Sajid, these were some of the initial ideas I wanted to share with all of you about how we can bring in some of these concepts about how humans program and build this inside our synthesis engines to be able to perform more intuition-based program generation rather than search, and also to be able to understand different modalities and be able to learn to decompose the problem into smaller chunks. So these were just some initial attempts we have been looking at, and I should believe there's long way to go to actually build both biases in terms of architecture itself, what type of architectures we develop, but as well as what type of semantic information we encode and use to generate more and more complex programs. So this was mostly it. Thanks a lot, and I'll be happy to answer any questions.
Thank you. So that's an awesome talk. So one question that people have is that, so many of the algorithms that you have been describing in this talk, they mostly fall into this group of neural program synthesis algorithms. So however, it seems that neural network-based algorithms usually do not generalize very well combinatorially or systematically. So one example is that because of the fact that nested loops and recursions brings an infinite number of possible programs in your program space that is defined by your DSL. So, but your training data can only be it's always finite. And how do you think how do you think you can combine different approaches, or how can you think you can improve the current neural network-based method to address this issue to have more systematic and combinatorial generalization? Thank you.
Yeah, actually, that's a very, very great question and very deep as well. Yeah, so I'll give a brief answer and we can discuss it more afterwards. So at very high level, actually, that's something we also observe when I had a one slide description about induction versus synthesis, where if we were to, let's say, we're training a neural Turing machine style architecture, or where we make everything differentiable and have the network do all of that work implicitly. So those actually we find they're harder to generalize to uh, more longer programs or more expressive tasks. Whereas actually here what we are doing is we are generating symbols as output from the network, um, and uh, and actually so let's say if our DSL has a recursive operator or a higher order function operator, then the network has the capability to emit that, and implicitly actually it can perform variable length computation. So let's say I have a function that takes as an argument how many loop unrollings do I want to do, or I have a function that takes a function as an argument. So now actually, and that has a termination condition. So now I can do arbitrary length computations, at least in theory, by using these symbols. So that's one benefit of actually using symbols as outputs rather than using network as the computation mechanism. Now, we have also seen some examples in robustville and other settings where we only train programs up to a certain length, and but they are able to generalize to programs of larger lengths. But the more general problem, I think, of doing very sophisticated reasoning about loops and recursion, uh, I think we need to explore more about how to build those type of biases or structure inside the network. And there's still a lot more work to do.
Thank you. We have another question from one of our other speaker, Kevin Ellis. Kevin, can you just unmute yourself and say your question?
Hi, yeah. So the sort of playful version of this question is, what can you learn from your niece? But the real version is, what kind of insights do you think we can get from like pedagogy in programming? Like, do you feel there's any sort of ideas we could pull there from how humans like start from being bad at programming to like learning to work on teams and do all the things human software engineers do. Like, is there ways we could generate data pedagogically when we're like making synthetic data for training these networks and things like that? What are your thoughts in this space?
Yeah, that's another great question. Yeah, so I guess one thing there is that some of the initial work which we were also doing was how students learn programming. So we were looking at data from these edX classes, how students are given exercises, and there are two settings. One is setting where they only get test cases just to say, oh, your program doesn't work here, go and fix it. Or the other setting where TAs actually come in and give qualitative feedback. We didn't do a very scientific analysis, but we did find actually that giving that type of feedback or automatically generating feedback, students were able to learn better in the sense they were able to finish exercises faster and actually solve more problems. So there's definitely some uh, lots of evidence, and that's how we also learn in classrooms as well, that teachers actually tell us conceptual problems about what's wrong with our programs and how to fix it or how to generally think about it. So there's definitely actually lots of room about getting better feedback and incorporating better feedback in terms of concepts about programming rather than just test cases. This Karel example I was showing you about looking at semantic execution feedback, that was a very small example of how can we go beyond these types of just synthetic test case based learning. But we definitely need more interesting architectures as well as feedback mechanisms to see what type of information we might want these learners to give, that they can actually generalize much better than be able to just generalize a little bit about changing one or two operators, but actually learning something more fundamental and more general.